Okay, I'm going to finish section 8.1. I did not have time to complete it in class, and so I'm going to pick up where I left off. All right, so we left off in class with finding the nth term rule of a sequence. Now I just want to look at a couple more here. If I have the sequence and I want to write the nth term rule for the sequence, a rule that would generate any term of the sequence, what I have to do is I have to concentrate on the relationship between the term index and the actual value of the term. So here's the first term, second term, third term, fourth term of the sequence that's provided. One way you could do this is you could break it up, since we have fractions here, you could break it up into the numerator versus denominator. So let's look at the relationship between the term index and the numerator. Notice the numerator of the first term is 1, the numerator of the second term is 4, 9 is the numerator of the third term, and 16 is the numerator of the fourth term. So we ask ourselves, what would we do with this index of the term in order to actually generate the numerator value? In other words, what would you do to 1 to get 1? What would you do to 2 to get 4? What would you do to 3 to get 9? What would you do to 4 to get 16? Well, with some thought, we realize that these numerators are really perfect squares. And in fact, the numerator is really the perfect square of the index of the term. 4 is a perfect square of 2, 1 is a perfect square of 1, 9 is a perfect square of 3, 16 is a perfect square of 4. So in general, the numerator of the nth term is going to be n squared. Now let's look at the denominator. The denominator of the first term is 5. The denominator of the second term is 25. The denominator of the third term is 125. And the denominator of the fourth term is 625. We notice that all these denominator terms are factors of 5. And in fact, upon further thought, you can see that each denominator is nothing more than the square of 5. Or each subsequent term of the denominator is a square, is 5 raised to some power. So if I raise 5 to the first power here, the index of this term, I generate 5. And if I raise 5 to the second power, which is the index of the second term, I get 25. 5 to the third power, index of the third term is 125, and 5 to the fourth power, the index of the fourth term is 625. Another way you can more readily see a pattern here is if you factor 5 out of each of these denominators here. Here you can see you have 5 to the first power, 5 to the second power, 5 to the third power, and 5 to the fourth power. So in general, the nth term of the denominator is going to be 5 to the nth power. So far, what we've accomplished here is that our nth term rule for this sequence, the numerator is going to be n squared, and the denominator is going to be 5 to the nth power. Now, we also have this sequence alternating in sign, positive, negative, positive, negative, positive, negative, positive, negative. And notice the odd terms of the sequence are to the positive power, and the even terms of the sequence are to the negative power. And so therefore, we would have to, in order to account for this alternation in sign, we would have to have -1 raised to a power. So notice, if I raise -1 to an odd power, I get a negative, when in fact, our first term of the sequence is positive. When I raise -1 to the second power, I would get a positive, when in fact, the second term is negative. So we're going to have to ensure that when I raise -1 to an odd power, I get a positive. And when I raise -1 to an even power, I get a negative. To ensure that to happen, I am going to have to raise -1 to the n+1 power. Because -1 to my first term here, when the index of the term number is 1, would have me saying -1 to the 1+1 power, which is -1 to the second power, which is a positive term. If the index of the term is 2, 2 plus 1 is 3, -1 to the third power would have me saying the second term is a negative. And when the index of the term is 3, 3 plus 1 is 4, -1 to the fourth power would have me saying the third term is positive, etc., etc. So therefore, the nth term rule for this sequence is going to have to be this. That would be the nth term rule here. This nth term rule would generate any term of this sequence here, and it also accounts for the alternation in sign too. All right, let's look at this next sequence here. So the first term of my sequence is -1, the second term is 4, the third term is -9, fourth term is 16, fifth term of the sequence is -25. Notice that each of these terms are perfect squares, all right? And in fact, to generate 1, we would square the index 1. To generate 4, we would square the index of the term 2. To get 9, we square 3. 16 comes from 4 squared. 25 comes from 5 squared. So to account for that, our nth term rule is going to have n squared. Notice the signs of these terms alternate. We go from a negative to a positive to a negative to a positive to a negative. And notice odd terms of this sequence are negative and even terms are positive. So to account for that, I would have -1 raised to the nth power, because -1 raised to an odd power is going to give me a negative, and -1 raised to an even power will give me a positive. This would be the nth term rule of that sequence. All right, to close out this section here, we're going to look at what is called summation notation. And summation notation is used to represent what is called a series of a sequence. So I'm going to lead up to the definition of a series. Given a sequence here, in general, if I have some sequence, then we say the sum of the terms of this sequence denoted as the sum of the terms of the sequence would be represented like this. So if I sum up all the terms of this sequence here, I have what is called an infinite series in mathematics. So a series is the sum of terms of a sequence. That's what a series in mathematics is. If I sum up just the first n terms of this sequence, then I have a finite series. So the sum of the first n terms of the sequence would just represent a finite series here. There should be a plus sign in here. So we're adding up the first n terms of the sequence. Sometimes we call this finite sum an nth partial sum of the sequence, an nth partial sum of the sequence. Now, instead of writing out a series in long form like this, oftentimes we use more compact summation notation. So to denote the sum of the first n terms of a sequence, we tend to use this sideways looking m character. This sideways looking m is called uppercase sigma. It comes from the Greek alphabet. Whenever you see this notation, you should be thinking sum. And if you take a course in probability and statistics, you will see this symbol a lot. Yeah. So this is called summation notation, and all summation notation has what's called an index of summation. Sometimes we represent the index by using the letter I or K or N. Those are typical values. But any variable down here could represent the index of summation. We have the initial starting point for index of summation, and we have some sort of a terminating point up here. So this summation notation is saying that I'm going to add together the first n terms of a sequence, where I starts at 1, then I increments to 2, then I increments to 3, then I increments to 4, I becomes 5, I becomes 6, I becomes 7, I becomes all the way to n. That's where I terminates. And this would be the nth term rule that we would put inside the summation notation. So this is a very compact way of saying that I would be adding together the first n terms of a sequence. This is a finite series. If I let my index of summation go to infinity, then this would be saying that I would have an infinite series where I'm adding together an infinite number of terms of a sequence. All right, let's evaluate some sums here. Now I'm going to use K for my index of summation instead of I. Okay, so this is my nth term rule of a sequence here. And this summation is saying I'm going to add together the first 5 terms of this sequence. So the first term is going to be 2 times 1 plus 3. Plus the second term of the sequence would be 2 times 2 plus 3. Plus the third term of the sequence would be 2 times 3 plus 3. Whoops. Plus the fourth term of the sequence be 2 times 4 plus 3. Plus, and then the fifth term would be 2 times 5 plus 3. All right, so this is going to give me 2 times 1 is 2 plus 3 is 5 plus this will be 7 plus 9 plus 11 plus 13. This is the sum of the first 5 terms of our sequence. So this is a finite sum, or sometimes we would call this maybe the 5th partial sum of our sequence. Adding these together here, 12, 21, 32, and we would get 45 for the sum here. So we get a sum of 45. All right, suppose we want to evaluate this sum here. All right, notice that regardless of what n is, the value of the sequence that we're adding together is always going to be 3. So this would be called a constant series here, which comes from adding terms of a constant sequence. So all these terms are 3. So when n is 1, we have 3, plus n is 2, we have 3, plus n is 3, we have 3, plus n is 4, we have 3. When n is 5, we have 3. When n is 6, we have 3, n terminates at 6. So this is re-added to itself 6 times, or we can more efficiently compute or evaluate this by doing 3 times 6, and we get 18. All right, let's try another one here. Let's add together the first 6 terms of a sequence whose nth term rule is defined to be this here. First, we let k be, actually, we're not adding the first 6 terms together. We're adding terms 3, 4, 5, and 6. Okay, so we start off by letting k be 3. So we'd have -1 to the 3rd power times 1 over 3, plus then k increments to 4, -1 to the 4th power times 1 over 4, plus -1 to the 5th power times 1 over 5, plus -1 to the 6th power times 1 over 6. Now, -1 to an odd power is going to be a -1. -1 to an even power is going to be a +1. So this is going to be a -1/3 plus 1/4 minus 1/5 plus 1/6. All right, and to add these together, we would need a common denominator, which is 60. Multiplying this by 20 over 20 to build it up to -20 over 60. Multiplying this by 15 over 15 to give us 15 over 60. This by 12 over 12 to give us minus 12/60. This will be a minus sign here. So we got minus 12/60. Multiplying this by 10 over 10 to give us plus 10/60. Okay, so now when we add these together here, -20 plus 15 minus 12 plus 10 gives us -7 over 60. And that would be the sum of terms 3 through 6 for this particular sequence. Now that would be the evaluation of this series here. Okay, so up to this point, we were given the summation and we were asked to actually evaluate it. What if we're given the summation written out in long form and we're asked to write it using more compact summation or notation or sigma notation? So what if we were asked to write this sum using summation notation? All right, this is an infinite sum, and we want to write it using our compact summation notation. First of all, we have to find the nth term rule here. So we need to be asking ourselves if the first term of the associated sequence is 1/2, the second term is 4/3, the third term is 9/4, the fourth term is 16 over 5. What in general would be the nth term? Okay. Well, again, let's look at the relationship between the index of the term and the numerator. What do we do to 1 to get 1? What do we do to 2 to get 4? What do we do to 3 to get 9? What do we do to 4 to get 16? After some thought, it looks like when you square the index of the term number, you generate the actual numerator. So our nth term rule is going to have n squared for the numerator. The denominator, what do you do to 1 to get 2? What do you do to 2 to get 3? What do you do to 3 to get 4? What do you do to 4 to get 5? Looks like the denominator is 1 ahead of the index of the term. So it looks like if I take my term index and add 1 to it, I will generate the denominator. So the denominator will be n plus 1. Therefore, this infinite series can be represented as k goes from 1 to infinity. We would have k squared over k plus 1. And that would be a way of representing this infinite sum using the summation notation. All right, let's look at this one here. How would I represent this infinite sum here? There's your first term of your sequence being added to your second term, being added to your third term. So this is an infinite series. How would we represent this infinite series using the summation notation here? Well, notice the numerator is always 1 ahead of the index of the term. So to go from 1 to 2, you'd add 1 to 1. To go from 2 to 3, you'd add 1 to 2. And to go from 3 to 4, you'd add 1 to 3. So it looks like the nth term rule of this sequence here is going to have the numerator be n factorial. Not n factorial, n plus 1 factorial. So this will be n plus 1 factorial. The denominator, what do you do to 1 to get 7, 2 to get 14, 3 to get 21? It looks like all these denominators are factors or multiples, are multiples of 7. 7 is 7 times 1, 14 is 7 times 2, 3 is 7 times 3. So it looks like if we take 7 and multiply it by the index of the term number, we generate the denominator. So it looks like the denominator would be 7n in general. All right. So therefore, to represent this infinite series, I would have n go from 1 to infinity, and I would have n plus 1 factorial over 7n. And we have written that infinite series using summation notation. Okay, there are some properties of summation, the summation operator. Basically, this is saying that if you sum up a constant number of terms of a sequence, where the sequence terms are all constant, just the same, from 1 to n, that means you'd be adding c to itself n times, which means n times c would be the evaluation of that summation. This is saying that if you take the summation of a constant times the terms of a sequence, you can rewrite this equivalently as the constant times the sum of the terms of the sequence. So this constant c, which is some real number, can be extracted outside of the summation notation. Finally, this is saying whenever you take the sum or the summation of the sum or difference of terms of two different sequences, it would be, you can rewrite it as the sum or difference of the summations of the individual terms of the individual sequences together. These are important properties that the summation operator enjoys. And ladies and gentlemen, what's interesting here is when you get into integral calculus, the antiderivative or the integral follow these same properties as the summation operator does, because the integral is really an infinite sum in calculus. All right, so that concludes section 8.1.